For this question, existence of discrete energy levels can be demonstrated by observing. The easy answer, right, is simply C, because emission absorption line spectra are supposed to be the evidence for the fact that energy levels within gaseous atoms are quantized. Okay, quantized means what? They exist, right, in discrete amount. Okay, so these are actually you see, whenever you see this means, right, that the energy of the atom, right, must be certain amount. Okay, it cannot be in other values. Think of it as a underground building. Okay, this underground building, right, there are many floors. All these floors are not separated by the same distance underground. Or the levels underground, right, get increasingly deeper. Okay, and occupants in this underground building, right, must only stay in these levels, underground levels. They cannot, for example, stay on the staircase, or it's not allowed. You are only allowed on the level itself. Okay, these levels also have some names. These are called bound states. Okay, and just to add on a little bit, whenever you see this as a ground state, right, okay, it's a ground state. This is actually, right, ground state of who? This is the ground state of outermost electron. Okay, so for emission absorption line spectra, right, we are actually talking about just the outermost electron getting excited, de-excite, hence absorbing or giving out photons. Okay, yeah, and it does not concern the rest of the atom, simply because, right, the energy that is at work, or when you are dealing with absorption line spectra, emission line spectra, is all very low energy. We are all using just visible light to excite this atom. So you can only excite outermost electron because, right, they are the highest in energy, so to speak. Okay, in the whole atom, the rest of the electrons are much deeper in, much more stable, and this underground building, right, extends much deeper. So visible light photons, right, couldn't excite other atoms, sorry, other electrons which are deeper in, can only excite this outermost electron. But anyway, that is just this. One more note, right? Why is it hot gases? Okay, gases, right, means, right, is the atoms are far apart. So we are all talking about atom by atom. Okay, so let me just write it out as isolated atoms. This is different from, let's say, right, the matter. Okay, so in contrast, right, in photoelectric effect, you still have the free state as 0. Okay, and all these levels are negative. But so this is negative how much? Work function. So these electrons in the matter, right, they are in a solid state. Okay, they are not in gaseous state, unlike the emission line spectra. So they are allowed, right, to occupy all these energy levels. You see, this is a continuum. Okay, versus, right, these are discrete, which is why, right, if you give these electrons, let's say the electron is the least tightly held. Okay, so this guy, he will be near the surface, sorry, near the upper bound of this continuum. So if you give it a photon, it make a jump, or it land here. Okay, and this amount, right, will be called the Ke max. But if you give another electron, right, the same photon, the same jump, he will land at a different spot. Yeah, and we don't call that Ke max, or we don't call the difference between that level and the 0 Ke max. Yeah, we only consider top guy. But the point I want to tell you is this: when things are in solid, right, their energy levels are different from when they are in gaseous. So that's why emission absorption line spectra, the material that is performing this phenomenon, right, must be the gaseous state. Okay, so every experiment, right, they have their own specific setup, and every experiment, you see some of these energy diagrams, okay, they all correspond only to that particular setup. So don't confuse this description, don't transfer the description from one case to another case because they do not apply. Okay,